Okay, everyone, assalamu alaikum. Let's begin. So we were doing arithmetic and geometric progression. We started this in our last session. Today, we are going to complete the concepts that we have in this topic. There's just one thing that's left. We will discuss that, and then maybe we can have a look at a couple of questions. Otherwise, we will do some more practice after the Eid break, inshallah. So after today, we should be done with all the concepts, all the P1 concepts. We will still need to do some more practice on circular equations. So we might need one class on that and also one class at least on APGP. It might be a longer class in which we discuss any problems that you have from this worksheet. Okay, but before that, I would expect that you have attempted all the assigned questions at least from the worksheet and maybe more from recent papers as well, so that you can let me know if there are any problems. Okay. So let's start with this. First of all, we started with arithmetic progressions last time. So I'll just quickly remind you about that. So what is a progression? Progression is just another word for sequence that we've done in O-levels as well. But now in A-levels, we only have two types of sequences. One is arithmetic and the other is geometric. Arithmetic sequence is basically a sequence in which the difference between consecutive terms is constant. It's defined by two things: first term and common difference. How do you find difference? Next term minus the previous term. There's a term formula that we use for this to find a specific term in the sequence. That's a plus n minus 1 times d. And then we talked about two sum formulas. One was this: half n into 2a plus n minus 1 into d. You can find the sum of the first n terms using this formula. And also, we had another formula, Sn equals half n into a plus l. This is how it's written in the formula sheet. Now, L here basically means the nth term. So if you're looking for S7, for instance, the last term in this formula would basically be the seventh term. T7 would be L basically, right? So another way to write the same formula could be like this. We could say it's half n into a plus tn. In the formula sheet, it says L. So you need to understand what L stands for there. It's the nth term. All right. So we looked at how we can use this formula as well yesterday. This is how these formulas are written in the formula sheet. Then we talked about how you can find sum of terms between two terms. For example, if you have a sequence like this, it's an AP with first term 105 and difference equal to 7. And what we were looking for was sum of all the terms starting from the 10th term to the 35th term. All right. Now, how do you find sum of all of these terms? We said one idea could be that you find the sum of all 35 terms, subtract from that the sum of the first 9 terms, and that will give you the sum of the terms from 10 to 35. All right. So this is how we said we could find sum of all the terms from the 10th term to the 35th term. That's what we did yesterday. And then there was this relation that we said we also need to know about. If you have an arithmetic progression and you know 3 consecutive terms from that AP, you can say T2 minus T1 should equal T3 minus T2. So B minus A in this case should equal C minus B. All right, so these were all the concepts that we talked about yesterday as far as AP was concerned, arithmetic progressions. Then we talked about geometric progressions. What are geometric progressions? These are sequences in which the ratio between consecutive terms is constant. So you have to basically multiply or divide by the same number to get the next term. Right, so this is also defined by first term, but along with that, you have ratio. How is ratio calculated? Next term divided by previous term. Take any two consecutive terms, divide the next term by the previous term, and that gives the ratio. And these are the term formulas and the sum formula for a GP. AR raised to power n minus 1. This is the term formula. You can find a specific term using this formula. And this is the sum formula: A into 1 minus R raised to power n divided by 1 minus R. Here you have to be careful that the value of R that you write, it should be written inside brackets, especially if it's negative. Otherwise, you'll end up doing careless errors. These are the two formulas that we talked about in GP. The ratio could be less than 1 sometimes as well. So in this case, 8/16, that gave us ratio, which was 0.5. Ratio can also be negative sometimes. In this case, the ratio was negative. You can also find nth term formula for a GP like this, right? So we talked about this. This was important: percentage increase and percentage decrease. So you'll find a lot of questions in which you'll have a number that is being increased by the same percentage or decreased by the same percentage. And whenever you have a case like this, when you have a same percentage increase every time, same percentage decrease every time, this would always be a geometric progression. Always be a geometric progression when a number is being increased or decreased by a percentage. Since it's a GP, you should be able to find the ratio of such sequences. If there's a 5% increase, you can think of it like this. It was 100% initially, 100%. After 5% increase, it will go to 105%. What is 105% in decimals? It's 1.05. Okay. Similarly, if it's a 7% decrease, that means if the original number was 100%, after a 7% decrease, it would go to 93%. What is 93% in decimals? That's 0.93. Okay, so that's how you find ratio when you have a percentage increase or percentage decrease. Another way to think about this could be it's a 7% decrease. So if you just write down the sequence like this, that okay, if the first term was 100, the next term would be 93. So 93 over 100, that gives you 0.93. So you could think of it either way, but you should be able to write down the ratio in case you have a percentage increase or a percentage decrease. And then the last thing was, if you have 3 consecutive terms in a GP, and one of them is unknown, or you want some kind of relation between these terms, you can say, since the ratio is constant, the ratio can be found by dividing the second term by the first term, or also by dividing the third term by the second term. So that gives you this equation. And that's something that you can generalize. If you have 3 terms like this, A, B, C, B over A is always going to be equal to C over B in case of a geometric progression. Okay, so this is also something that you'll find useful when you do some questions. Okay, so these are all the concepts that we did in the last session. Now there's one thing that is left, and that is sum to infinity of a geometric progression. Sum to infinity of a geometric progression. Now let's talk about this. Let's talk about what the sum to infinity of a GP is. Now, what does that mean? What does that statement mean in the first place? Sum to infinity. What's infinity? Infinity is basically an extremely large number. We can't put a value to this, but we just say it's an extremely large number. So it's a number that you can't possibly write because it's so big, you can't even think of it. So you can't put a value to this, but you just think of it like this, that it's just something extremely large. Okay. So for instance, we've talked about cases like this. When you have 1 over x, for instance, if x was to approach 0, if x was to go towards 0, this number would become extremely large. The smaller this number x becomes, the larger this whole fraction is going to be. It's going to go towards infinity. We talked about the concept of infinity in functions earlier as well. But for now, just understand that infinity means an extremely large number. Okay. Now, what we want to do is we want to find sum to infinity of a geometric progression. Now, first of all, sum to infinity does not exist for an arithmetic progression. So what does sum to infinity mean in the first place? Let's talk about that. So sum to infinity basically means, for example, if you had a progression like this, 2, 5, 8, 11, 14, and so on, and this sequence was to go on forever like this, what would be the sum of all of those values? Well, if the sequence was to continue like this forever, at some point, these values are going to become very large, because it's an AP. You keep adding 3 to it, you keep adding 3 to it, it's going to become extremely large. Sum of all of these values is also going to become extremely large. So you can't put a finite value to this. There's no sum to infinity of an AP. So sum to infinity means that if a sequence was to continue forever, right? If there was no end to a sequence, what would be the sum of all of those values? For an AP, this sum is not going to exist, right? Because the sum will either go towards positive infinity. In this case, it's going to go towards positive infinity. If you had another sequence like this, if you had, for instance, 50, 47, 50, 40, 30, 20, 10, 0, minus 10, minus 20. This sequence is going to go towards negative infinity. So for an AP, the sum to infinity, that means sum of all the values in this sequence, it would either be positive infinity or negative infinity. If the difference is positive, it would be positive infinity. If the difference is negative, it would be negative infinity. So for an AP, the sum to infinity is not going to exist. So we are just going to focus on geometric progressions. So we're only going to talk about sum to infinity of a GP, not an AP. Now, what about a GP? Let's say you have a geometric progression like this. Let's say you have 2, 6, 18, 54, 162, and so on. If you had a sequence like this, this is a geometric progression. You're multiplying each term by 3 to get the next term. Now this as well, you can see, since the values are becoming larger, you have 162, then you have that multiplied by 3, then that multiplied by 3. This is also going to go towards infinity. So this also does not seem to have a finite sum as such, because the values are increasing. However, if you had something slightly different, if you had something like this, if you had a GP that looked like this, 16, 8, 4, 2, 1, 0.5, and so on. Now in this GP, you see, the values are becoming smaller and smaller. They're not increasing, they're becoming smaller. If you were to, now, if this sequence was to continue forever, it'll go like this, 0.25, 0.125, and so on. And eventually the values are going to become very, very close to 0. If you were to add all of these numbers, this sum is going to be finite. It is going to have some specific value. Now, even though the sequence is continuing forever, now since the values at some point are going to become extremely small, the sum of all of those values, that is going to have a finite value. Okay, now let's try to understand how that happens. Let's say you've got this geometric progression. Can we write down the first term of this GP? First term of this GP is 16. The ratio of this GP, 8 over 16, that's 0.5. So we know the first term, we know the GP. Now think about this. If you were finding the sum of the first few terms of the sequence, let's find the sum of the first 4 terms, for instance. Let's see what that turns out to be. Remember the sum formula? What was the sum formula? Sn equals A into 1 minus r raised to power n divided by 1 minus r. What does that give you? S4, that's A, which is 16, into 1 minus 0.5 raised to power 4 divided by 1 minus 0.5. Let's evaluate this and see what this turns out to be. Can somebody do this for me? What does this number turn out to be?
30.
Sorry?
30.
30, okay. Sum of the first 4 terms is 30. Okay, if we use this formula, sum of the first 4 terms, or in fact, we can just add them up like this as well. The sum is 30. Okay, sum of the first 4 terms is 30. Now let's try and find the sum of the first 6 terms maybe. Let's see what that turns out to be. 16 into 1 minus 0.5 raised to the power 6 divided by 1 minus 0.5. Let's see what that turns out to be. Sum of 4 terms was 30. What about the sum of the first 6 terms now? 31.5. Sum of the first 6 terms is now 31.5. Okay, so sum of the 6 terms is 31.5. Let's find the sum of the first 10 terms. Let's see what that turns out to be. 16 into 1 minus 0.5 is to the power 10 divided by 1 minus 0.5. What do you get for that? Sum of the first 10 terms now. Now this is turning out to be 31.96875. 31.96875. Okay. Now what about sum of the first 20 terms? Can you figure that out? 16 into 1 minus 0.5 raised to the power 20 divided by 1 minus 0.5. What's this? What's your calculator giving you? Okay, now this is turning out to be 31.9999 and then 6948. You see, the sum is kind of getting stable now. It's not changing much. Let's try, for instance, sum of the first 30 terms now. Let's see what the calculator gives now, or in fact 50. 16 into 1 minus 0.5 raised to the power 50 divided by 1 minus 0.5. When you do this, your calculator gives you 32. Now, it's not going to be exactly 32. It's going to be something like this. 31.999999999, and then maybe a few more nines. Now, since the calculator has a certain level of accuracy, it can only show you like 10, 11 decimal places, not more than that at max. Since up to that many decimal places, if you the calculator can't show this whole number, it rounds it off to 32. But what's happening is, you can see the sum of the first term was 16. Sum of the first 2 terms was 24. Sum of the first 3 terms is 28. Sum of the first 4 terms is 30. Then 6 terms is 31.5. Then 10 is this. 20 is this. And at 50, it's basically very close to 32. And if you would try any other number now, even if you were to try S100 now, some of the first 100 terms, you would realize that's also 32. It's not changing anymore. So sum to infinity means that if this sequence was to continue forever, we say S infinity, what would be the sum of all of these values? We can look at the pattern already from this. When we're adding a relatively large number of terms, since the terms after this point, they're going to be very small. At some point, they're going to be like 0.0000 something. They're not going to make much difference to the sum. Eventually, if you were to add all of these values, the eventual sum of all of them is going to turn out to be 32. Now, that is the concept of sum to infinity. Okay, that's the concept of sum to infinity. That if you were to add all these terms in this sequence, what would be the sum of all of them? Okay. Now, that's the concept. That's the idea of sum to infinity. But now, this is a long process, trying to understand the pattern and figuring out what the sum to infinity turns out to be. Well, we basically have a direct formula for finding sum to infinity. Let's discuss it quickly. But before that, let's compare these two geometric progressions. For the first one, we said that the sum to infinity does not exist, right? Because the values are becoming larger. In the second case, the sum to infinity existed, Why? Because the values were becoming smaller. So sum to infinity is only going to exist if the values in the sequence, in the geometric progression, they were becoming smaller and smaller like this, such that they eventually become very close to zero. If they are becoming larger, like in the first case, then the sum to infinity is not going to exist. So how do you know if the values are going to become smaller and smaller or larger and larger? Think of the ratio. In the first case, the ratio was 3. In the second case, the ratio was 0.5. When you multiply by a number, multiply something by 3, the number becomes larger. When you multiply something by 0.5, the number becomes smaller. When does the number become smaller? A number becomes smaller when you multiply it by a ratio, a number between -1 and 1. In terms of its magnitude, the number is going to keep getting smaller and smaller if the number that you were multiplying was between -1 and 1. In terms of its magnitude, if it's less than 1, the magnitude of the number becomes smaller and smaller, and eventually it's going to become close to 0. Okay, so sum to infinity is only going to exist when the ratio is between -1 to 1. Now keep that in mind and think of the sum formula. Remember what the sum formula was for a GP. The sum formula was a into 1 minus r raised to the power n divided by 1 minus r. This was the sum formula for a GP. Now, if the ratio was between -1 and +1, if the ratio was between -1 and +1, what would happen to this thing, r raised to power n, if you were to find sum to infinity? What would the sum to infinity look like? Sum to infinity would be a into 1 minus r raised to power infinity divided by 1 minus r. Let's write it below there. So using the sum formula, if you had to find sum to infinity, this is what it would look like, right? 1 minus r raised to power infinity divided by a into 1 minus r raised to power infinity divided by 1 minus r. Now, if the ratio is between -1 and 1, what is this going to be? R raised to power infinity. Think of a number between -1 and 1. So for example, between -1 and 1, the ratio that we saw above, that was 0.5. So the ratio was 0.5. 0.5 raised to power an extremely large number. So raised to power 1, it will be 0.5. If it was 0.5 raised to power 10, can you tell me what that number is? 0.5 raised to power 10. What do you get from that?
9.765 times 10 to the power of -4.
9.65?
765. 766 to be if you round.
Okay, 9.766 into 10 raised to power -4. 0.5 squared was 0.25. You see, the number is becoming smaller and smaller. If you were to do 0.5 raised to power infinity, this number is actually going to be very close to 0. So this number is going to go close to 0 like this, right? So if you take a very high power, a very large power of a number between -1 and 1, what happens is it goes towards 0. So in this formula, if r raised to power infinity goes to 0, what are we left with? We're just left with s infinity, that equals a into 1 minus 0 divided by 1 minus r, and that gives you sum to infinity equal to a over 1 minus r. And this is the formula that we have for sum to infinity. Sum to infinity of a GP is given by a over 1 minus r. And the condition for this formula is that r has to be between -1 and 1. The sum to infinity only exists when that condition is met. This is the sum to infinity formula for a geometric progression. Sum to infinity equals a over 1 minus r. So in that Sn formula, if we just get rid of this part, this is the sum to infinity formula. And why do you get rid of that part? Because when n is infinity, this becomes 1 minus 0, and that's just 1. You can just get rid of that, and you're left with a over 1 minus r. That's the sum to infinity formula. Now, what we've discussed until now was just the background of this, what sum to infinity means, and when does it exist, when does it not exist, how can we get to this formula. But now what you actually need to use in the exam is this formula. This is given in the formula sheet. Now you understand the condition for this as well, that this formula can only be used when r is between -1 and 1. In the formula sheet, it writes the same condition as modulus of r. So the formula sheet will write something like this. It will say modulus of r is less than 1. Right? That's the same thing as this. It's between, r is between -1 and 1. So this is modulus function. You will learn this later in paper 3. Learn more about this in paper 3 later. But for now, this condition that's given in the formula sheet, just know that this translates to r between -1 and 1. Okay, so the formula sheet will write something like this. You would understand it as this: r is between -1 and 1. Sum to infinity only exists in this case. Okay, so that's the idea of sum to infinity. Now let's go back to the sequence again, this geometric progression, and let's use the sum to infinity formula to find the sum to infinity of the sequence directly. So we looked at the pattern earlier to figure out the sum to infinity. Now that we know the formula, we can find that sum directly. So we have a GP in which the first term is 16 and the ratio is 0.5. How do you find sum to infinity of this GP? A over 1 minus r. That means 16 over 1 minus 0.5, and that gives you 32. And that's what you got above as well. That's the sum to infinity of this GP. Okay, now let me write down another sequence. Let's say you have another GP, another geometric progression, and that looks like this. Let's say you have 625 minus 125, 25 minus 5, 1 minus 0.2, and so on. This is what the sequence looks like. Now, this is also a GP because the ratio between the terms is constant. You can find the ratio like this. You can say the first term is 625. The ratio is minus 125 divided by 625, and that gives you minus 1 over 5, which is minus 0.2. That's the ratio between these terms. That's a constant ratio. So it's a GP. Now, since this ratio is between -1 and 1, the sum to infinity for this is going to exist. Well, how do you find that sum to infinity? The formula looks like this. Sum to infinity is a over 1 minus r. A is 625 divided by 1 minus r. What's r? R is minus 0.2. So it's 1 minus 0.2. What do you get from this? 625 divided by 1.2. 520.83. That is the sum to infinity of this sequence. So if this sequence was to continue forever like this, the sum of all the values in that sequence, that is going to be 520.83. Now, Okay, I'm sorry. I think I'm back now. Can you confirm this?
Yes, sir.
Yes, sir.
Okay, good. Thank you. All right. So I was basically saying sum to infinity of a GP only exists when R, the ratio is between -1 and +1. Okay, that's the condition for a GP, for the sum to infinity of a GP existing. Now, there's another terminology that you will see being used sometimes, and you would need to know about that, and that is convergence of a GP. Convergence of a GP. Now let's write down a GP here like this. So we have, for instance, 25, 5, 1, 0.2, 0.04, and so on. You can see the values are becoming smaller and smaller. It's a GP with its ratio between -1 and 1. In this case, the ratio is 0.2. The values keep getting smaller and smaller. Eventually, what's going to happen is these values are going to approach 0. We can say the sequence is converging to 0. Okay, the sequence is converging to 0. It's basically approaching a constant value, which is 0. Let's take another sequence. Let's say you've got something like this. You've got 50 minus 25, 12.5, minus 6.25, 3.125, and so on. You have a sequence like this. Now, in this case as well, even though the sign is changing, the first value is positive, then you have negative, then positive again, then negative again. In terms of magnitude, the values are becoming smaller. And eventually what's going to happen is, if we keep repeating this process, we keep dividing by 2, eventually the sequence is going to converge to 0. Okay? Eventually, the sequence is going to converge to 0. So this is another terminology that you need to know about. A geometric progression converges to 0 when R is between -1 and 1 as well. So the same condition that applies for sum to infinity applies for convergence of a sequence as well. So these two sequences, these are convergent sequences, as opposed to another sequence that we wrote above. I think it looked something like this: 2, -6, 18, -54, 162, and so on. This is going towards either positive infinity or negative infinity. This is not converging to 0. So the first sequence that you can see on the screen now, we would say this is a divergent sequence. Now that terminology is not that important because you mostly need to know about convergence. But the opposite of convergent is divergent. The first one, you would say it's a divergent sequence. The second one, this is a convergent sequence. It converges to 0. The third one as well, this is a convergent sequence. It converges to 0. How do you identify if a GP in particular converges or not? The ratio has to be between -1 and 1. So sum to infinity also exists when this condition is met, and convergence of GP also happens only when ratio is between -1 and 1. Okay, so these were the important concepts that we wanted to do today. First of all, how to find sum to infinity of a GP. A over 1 minus R, that's the formula that we have for this. Ratio has to be between -1 and 1. We looked at some examples of that. Sum to infinity only exists when ratio is between -1 and 1, and sequence is also convergent when ratio is between -1 and 1. the ratio is between -1 and 1. Okay, and that completes the arithmetic and geometric progression concepts that we have. And now you can do some practice questions. We're going to end this here for today. I will upload the worksheet. I think I haven't done that yet. I'll upload the worksheet so you can start working on the questions from that worksheet. Did I upload the worksheet or not?
You did, sir.
You uploaded.
Okay, so it's uploaded. You can start working on that. You have now 6-7 days for it. Our next class is going to be most likely on Tuesday. Yeah, so on Tuesday, we will have our next class, Tuesday and Wednesday, both days. Next Tuesday and then Wednesday. And in both of those classes, we will just be doing practice questions. We're done with it in terms of concepts. In one of the sessions, we could do some circle equations questions. And then, and the other one, which might be a slightly longer session for APGP, we could do practice questions on arithmetic and geometric progressions. I expect you to attempt the assigned questions from both the worksheets, and also, in addition to that, any other recent questions that you have. Okay, so make sure that you are that you have practiced before that class, so you know where you're having problems, so we could discuss them in class. Okay. Any questions before we end? No questions. So in terms of concepts, we are done. All right. This is all that we had in paper one. I hope you found this crash course helpful. Of course, we are not ending it yet. We will do more practice. But in terms of concepts, you're done. So if you have any feedback, you can let me know about that as well. I also have a past paper session starting from 13th of April. Any of you who's interested, you can let me know. The discount is valid for you guys, those of you who are part of the crash course, until the end, whenever you want to do it. Otherwise as well, you're always welcome to post your questions on the WhatsApp group. If you have any at any point before the exam, try to help each other out as well. If somebody posts a question, try to respond to that. That will be good for your own practice as well. If nobody responds, I will try to respond to your questions as well. But the way to do it is that when you post a question, you should post your working alongside that as well. That what you have attempted and where exactly you're stuck, so that I can pinpoint, okay, this is where you're going wrong and this is something that you could correct. Don't expect me to solve complete questions and post them regularly, because unfortunately the thing is, I have like tens of messages coming like this every single day, so it's kind of hard to respond to each one of them by solving the complete question. It's generally not possible for me because of my schedule. But you can help getting a quick answer by sending your working along with the question. If not, if you don't understand anything about a question, what I can do is I can give you a direction about it, then you can attempt it and then share with me your working and ask me where exactly you're stuck, and I can explain that to you. All right, so that's what we can do until your exam, inshallah, alongside. But now it's all about practice. If you missed any sessions, make sure that you watch the recording. You've got the notes available with you as well. They are going to be very helpful for you in your revision before exams. Please make sure that you have OneNote and OneDrive apps, both of them downloaded on your phone, because that is when the notes work best. I'm going to post their names again in this chat as well. You already know about these apps before. You need both of them downloaded. Otherwise, the link is not going to open in OneNote. OneNote files are basically saved in OneDrive. So the notes are only going to open in the app correctly if you have both of the apps downloaded, OneNote and OneDrive. Then you click on the notes link in the description. It will open in the OneNote app on your phone, and it will download all of these sections that you can see here. You'll have all the notes available. They will be very helpful for you in your revision because they cover all the concepts that you need to know about. All right, and then along with the practice questions that we've done, you should make sure that you keep revising, keep practicing, and that is what is going to help you in your final preparation now before exams. Okay, so that's it for today. If you have any quick questions, any other questions, you can let me know. No? Okay, good. So I'll see you again in next week then when we do some more practice then. I love this.